So our topic for this afternoon will be all about period of roll. Okay? So if you have a girlfriend, so the period of your girlfriend will be your basis for her mood. Am I correct? If you have a girlfriend. Huh? So the same as with the ship, we are going to use a different kind of period, not the period that has a blood, but when we say period, that is all about the time of rolling, ships rolling. Alright, so let us define first what is a rolling period, which is how a vessel quickly returns to its upright position while it is rolling. In other words, it is the time when a ship takes from the upright position. So take note that it is from the upright position. It is from its upright position going to a particular angle on the port side or on the starboard side, and then going back to an angle on the opposite side. So to give you a picture for wider understanding, if your ship is upright and then if it heels on the starboard side, and then the maximum heeling on the port side, I mean, and then uh, going to the opposite side on the starboard side, this is the maximum heel, and then it returns to become upright again. So that is the period, or the rolling period. Again, from upright position going to one side, then maximum, and then to the opposite side, and then upright. That is the rolling period. So we need a timer, no? If we are going to measure this one, because this is about only a few seconds. No? So the importance of rolling period to us mariners is to determine the metacentric height, or what we call as GM of the ship. And if we know the GM of the ship and the displacement of the ship, then we will be able to calculate or to estimate the moment of statical stability, in which it is the measure, it is the basis of stability at all angles of heel, meaning whether it is a small angle from 0 degrees to 15 and 15 or more large angles of heels. So this moment of statical stability is the basis. And again, when we say stability, that is the ability of the ship to return from its upright position. Alright, so what is the effect of different GM on the period of roll? So we have this stability nomenclature. Let's assume that the ship is heeling on one side. That is the base of the keel. And we have here the metacenter. Then that is uh, the center of gravity. So we have here kg, and then gm, then we have also km. So when the ship heels on one side, okay, so we have what we call as the righting arm or the GZ. If we have a large kg, or um, the position of the center of gravity is high, then we will be expecting that the GM will be small, no, of course. And as we have learned in our discussion in midterm, that GM and the GZ is proportional to each other. Therefore, if we have a small GM, then we will also have a small GZ. And the rule of thumb is if we have a small GC and small GM, we will have a slow roll or slow rolling period. And we call this one as tender. So we have a tender ship if that is the case. But if we have the center of gravity located near the base of the keel, or we have a small kg, or the center of gravity is located on the low side, we will also have a large GM. And it is proportional to GZ or righting arm. So we have also large righting arm. And it affects the rolling period to become faster. And we call this condition as stiff. Right? So let us repeat so that we will be able to be more familiar. A stiff ship, a ship that is said to be stiff when she has the following criteria: large GM, large GZ, and large statical righting moment. And its rolling period is short. So this is simple to memorize, because we have, when we say stiff, we have the letter S here, and when we say the effect of a stiff ship to its rolling period is short, then you have also S in the word short. Okay, so S and S, stiff, short, rolling period. Okay, so the disadvantages of a stiff ship. So even if we have a large amount of GM here, we still have the disadvantage. Okay, so the ship will not be able to immediately drain the water on deck in event where the ship encounters huge waves, which can virtually rise the center of gravity above the base of the keel. The ship watertight integrity of the ship will also be put into test. The tendency to sink of this stiff ship if the watertight integrity fails. So as you can see, the ship, if it will be said as a stiff ship, it will no longer have the capacity to ride the waves, but instead it will have the resistance. That is why we have only a short rolling period, thus it exposes the deck areas to the waves. That is why I am talking about the ship's watertight integrity. The same with this bulk carrier here. So if the ship watertight integrity fails, no, since we have a short rolling period only, and then the water, no, will not be drained as quickly as we have in a tender ship, then we will suffer a damage stability. Alright, for a tender ship, a ship said to be tender when she has a small GM, when she has a small GZ, and a small statical writing moment. Therefore, its rolling period is long. So, this one is also easy to memorize because when we say tender, uh, like the tender juicy hot dog, so we have the long, no? Long. So tender, long rolling period. Steep, short rolling period. So when I was still a college student like you, I have that in my mind that when we say stiff, that is small short rolling period, SS, and then tender for long rolling period. Now we have also the disadvantages of being a tender ship, that is to tendency to capsize due to negative GM because of the external force, which makes the vessel roll significantly. And we have also the lashing of rolling cargoes and containers will be put into test. So like what happened in this container ship. So if the ship will have a large, a large rolling period, or a long rolling period, if another wave will catch him, will catch the vessel, then it will add up to the um, healing of the vessel, and the securing materials will be put into test, like what happened in this container vessel. So we have, I guess we have a container jettisoned already. So also with this, what kind of vessel is this one? Do you know what kind of vessel is this? Yes, what kind of vessel? Okay, heavy lift cargos. Yes, heavy lift cargos, very good. So these heavy lifters usually also experiences small GM because they carry heavy cargos on deck. So that is why they have a long rolling period, and when it encounters waves, like if there is a wave which causes the rolling, and then there is another one, and then there's another one, so three waves consecutively, then it will add up to the healing angle. And as we have learned in our previous discussions, that it depends on the healing angle, the GZ or the writing arm will eventually become negative. Thus it makes or it will have the tendency of the ship to capsize. Alright, now for your information, we have the IMO standards for the metacentric heights. For all types of vessel, this is 0.25 meters. For bulk carriers, it must be at least 3 meters. But for bulk carriers, we will not have a problem with the metacentric height because the ship is designed to have a large amount of GM when it will be fully loaded, because all of the cargoes will be stored on deck. Will be stored in the holds, not on deck. For lug ships, okay, so we have 0.5 meters. Okay, so we have the picture or examples of ships with large GM. So again, bulk ship is designed when it will be fully loaded. We will have a large GM. We will also have a large GZ. Thus, we will also have a short rolling period. So we will have the resistance in this waves or adverse weather. But again, please be reminded of the disadvantages. Also for a tanker ship, so the same principle applied with a bulk ship. Now, there is an incident, if you can still remember, the bulk Jupiter, I guess, if you can still remember, which sank at the coast of Vietnam. So that incident was caused by the cargo, which has the tendency to become a liquid. That is the bauxite, no? So the ship was not certified to carry bauxite or cargoes which might liquefy, but bauxite that time is not yet considered as cargoes which might liquefy. That is why when it liquefied on that ship, of course, because that ship is not designed to carry liquid cargoes. When we say designed to carry liquid cargoes, we have a lot of bulkheads, no? As you can still remember in our discussion during prelim. So if we have a bulkhead, the purpose of having a bulkhead is to reduce the free surface effect. So if we have a free surface effect from all of these holds, then it will be deducted to the GM. So even if we have a large GM, as I have mentioned to you, since we have a large initial GM after loading, so if that bauxite will become liquid, and the holds normally will not be loaded 100%, only 80 or 70%, because this bauxite has a storage factor which can only fill up to 70 to 80% of each holds. So that is why if it is not designed to carry such cargo, then the tendency is it will sink because of the free surface effect. So as of this moment, it was already I guess revised by IMSBC code. No? Alright, so we have ships with small GM. So as you can see, we have a small GM because there are cargoes on deck. So basically, if we have a ship that carries cargoes on deck, automatically we can say that the GM of the ship will eventually become small. Yes, if we have a small GM, we will have a small GC. If we have a small GC, we will have a long rolling period. And be careful again with uh, the negative side or the disadvantage of having a small GM. So shapes with small GM, again we have a car shape. Huh? So the rule of thumb, if the value of GM is small, the rolling period is long. If the value of GM is large, the rolling period is short, meaning they are inversely proportional to each other, GM and rolling period. Alright, so what can we get from this? Meaning if we have a small GM, a very small GM, and we have also a very large GM, that would be a disadvantage for the ship. So probably as future chief officers, master, we shall make sure that we have the amount of GM necessary for the voyage, not so long and not so small. Okay, so just stay in between. That is the challenge of becoming the chief officer, because you will be the one to decide the stability of your ship. Alright, so we have here the rolling period formula. For English system, we have 0.44, that is constant, and for metric system, we have 0.797 times the beam divided by square root of GM. So this is what I am talking to you a while ago in the second slide. After the introductory slide, I have mentioned to you that we can obtain the value of GM by means of getting the rolling period by having only a timer. No? So simply by using your cellular phone, you have the timer there. So you will you can obtain already the rolling period of your ship. So we have here, alright. So we have the problem, sample problem. You are on a vessel that has a metacentric height of 4 feet and a BM of 50 feet. What can you expect the rolling period of the vessel to be? So this is something to do with the anticipation. So if you will be the master of the ship, then uh, you will give the instruction to the officer of the watch that if in case the rolling period anymore is not normal. So what is normal? By simply calculating the initial GM, the initial GM, the bread, and then the constant, you can obtain the rolling period, the expected rolling period. So if exceeds the rolling period, then like for example, in event that the ship encounters heavy seas, then that is the call of the master. No? What I mean to say is it depends on his decision whether the ship will have another course, because as we have discussed in the last week discussion about the windage, so we can control the ship's course, we can control the ship's speed in order for us to make the situation favorable. Okay, so it depends on the master. It's the master's discretion already. So we have the rolling period, which is 11 seconds. So the breadth of the ship is simply the width of the ship. So we have this one in our uh, ship particulars. The breadth, the length overall. Okay, so we have this information already. So again, we can use this formula if we have already obtained the rolling period. So we can get the GM. Alright? So again, if we have a metric system, so 797, uh, in replacement for the English, which is 0.44. Now, for the rolling period in still water, this has something to do with the inclining experiment done after the ship will be dry docked and before the ship will put into service, like if the ship is newly built. So this is the formula used by the naval architects to determine the rolling period. Alright, so we have there the formula 2 pi k, which is the radius, divided by pi g, small g, which is constant, 9.81 meter per second squared, times the ship's GM. So in order for us to further understand the formula, we have here the example. Find the still water period of roll for a ship when the radius of gyration is 6 meters. This radius of gyration is the distance in which the object inside the ship, a heavy object inside the ship, like for example, we have the crane, and then we have a drums of water, no, and then we have the weight, the given weight, and then we will be shifting it from time to time so as to create a momentum where the ship will roll in still water. So as I have mentioned to you, this has something to do with the inclining experiment, right? So we have the GM, which is 0.5 meters. So before the ship will be put into service, so it should be tested so as to prove that the lightweight condition of the ship meets the requirements of the convention, the different conventions, as well as it doesn't have any conflicts with the shape stability booklet, because might as well that the shape had some alterations, or there are some changes to the ship structure. So that is why when it needs, no, to be double checked if we can still use the same stability booklet, or it should be amended again. So we have 2 pi k divided by square root of g, small letter g, which is constant, times gf 0.5. So we have 37.69911 divided by 2.2, then that would be the rolling period. Alright, so this is the formula used by the naval architects. So we will not use this one, but at least we know upon the execution of the writing arm, at least we know already we have the idea of what is the formula for the rolling period. Because if you will be the chief officer, you will be the one to double check the work of your naval architect, assigned naval architect. So again, this is very useful. But I did not see the chief officer and the naval architect argue about this, because a lot of chief officer only say no problem. Okay, so we have the question, how can we obtain the GM to get the rolling period? If we wanted to get the rolling period before we sail, the expected rolling period before we sail, then we have the initial GM by simply referring to our quarter mean. So again, this is just a continuation of discussion. So if we have the draft survey and then we have the quarter mean already, then you can trace it in our shape stability booklet, specifically in our hydrostatic table, where you can see there the LCG, the equivalent LCG for the quarter mean, and then you have also the equivalent KML, which is the height of the metacenter above the base of the keel. Then the height of the center of gravity above the base of the keel, represented by LCG. So you just need to subtract the two and you will obtain the value for GM for the anticipation. Okay? But again, when the application for this one is most is significant when the ship um, experiences adverse weather condition, big waves, it experiences big waves, and then we need to determine the GM by using the rolling period formula. So we have to get first the rolling period, then we have already the breed of the ship, then we can already calculate the ship's GM. So it could be used in either way, anticipation or actual. All right, do you have any question?